Section 1. The Unfinished Revolution. Why we need new physics. We need new laws of physics. This is not just a quiet thought whispered in a laboratory late at night. It is a bold declaration for all of humanity. The rules we have now are brilliant. They have given us the modern world. They power our smartphones. They build our skyscrapers. They guide our airplanes across vast oceans. They are the foundation of our technological society. But these rules, as powerful as they are, do not hold all the answers. They are incomplete. To solve our biggest problems and to build a future that is truly transformative, we must discover new, more fundamental laws of nature. What exactly do we mean when we say laws of physics? Think of them as the universe's instruction manual. These are the core principles that explain how everything works, from the smallest atom to the largest galaxy. Isaac Newton gave us the rules for motion and gravity on Earth. James Clerk Maxwell unified electricity and magnetism. Albert Einstein gave us a deeper understanding of gravity, space, and time. These laws are not just abstract ideas, they are tools. They provide order. They allow us to make predictions. They empower us to build the technologies that define our lives. However, this magnificent instruction manual has missing pages. Section 2. The walls we've hit. The limits of our current rules. Imagine you are building with a set of toy blocks. At first you can build amazing things: houses, towers, bridges. Your creations get more and more complex. But eventually you realize you have run out of certain shapes. You cannot build a perfect sphere or a smooth, curved archway because you only have square blocks. This is where we are with physics today. Our current laws are like those square blocks. They have allowed us to build the magnificent structure of modern science and technology. But we are now trying to build things that require new shapes, new principles our current toolkit does not contain. We have reached a wall. This wall is most obvious in our quest to understand the fundamental forces of nature. We know of 4 forces: gravity, electromagnetism, the strong nuclear force, the weak nuclear force. The Standard Model describes 3 of these with incredible precision. It is one of the most successful scientific theories ever created, but gravity stands apart. Einstein's general relativity describes gravity beautifully on large scales, but it doesn't mesh with the quantum rules that govern the other forces. This separation is a fundamental limit. It tells us our picture of the universe is incomplete. This theoretical problem has very real-world consequences. We cannot fully predict what happens inside a black hole or understand the first moments after the Big Bang when everything was incredibly hot, dense, and small. These are not just cosmic curiosities. Understanding these extremes could reveal new forms of matter or new forms of energy. It could unlock secrets about the very fabric of space-time itself. Without a unified theory, we are like explorers staring at a map with huge blank areas labeled "Here be dragons." Section 3. Fading Dreams of Power, the Energy Conundrum. Our civilization runs on energy. It powers our homes. It fuels our industries. It connects our world. For centuries we relied on burning things: wood, coal, oil, gas. These fuels built our modern world, but they came at a great cost to the planet. We are transitioning to cleaner sources like solar, wind. These are fantastic steps, but will they be enough as demand grows? The dream of truly clean, virtually limitless energy remains elusive. Our current physics may not be enough to get us there. Consider nuclear fusion. The process powers the sun and the stars. It fuses light atoms to release enormous energy. On paper, it's the perfect energy source. Its fuel is abundant, found in seawater. It produces no greenhouse gases or long-lived radioactive waste. For over 70 years, scientists have chased a reactor that outputs more than it consumes. Controlling a star in a box is immensely difficult. We're pushing materials science and plasma physics to their limits. A breakthrough in fundamental physics could change everything. Imagine discovering a new particle, or a new principle that lets us control plasma with far greater ease. Maybe a new understanding of nuclear forces could reveal a shortcut to fusion, a way to achieve it at lower temperatures or lower pressures. Maybe new physics yields novel materials that withstand reactor heat and radiation, making engineering far simpler. This goes beyond fusion. What if there are forms of energy we don't even know yet? Theories say most of the universe is dark matter and dark energy. Mysterious stuff we can't see or touch. They don't interact with light. We know them only from gravitational effects on galaxies. If we understood the dark sector, could we tap it? Deep speculation, yes. But history shows understanding precedes harnessing. For decades, we have lived in a world defined by Moore's law. This was the observation that the number of transistors on a microchip doubles about every 2 years, making our computers exponentially faster and more powerful. This relentless progress has given us laptops, the internet, artificial intelligence, but this incredible era is coming to an end. We are approaching the physical limits of silicon. The components on our chips are becoming so small, just a few atoms across, that we are hitting a wall. At this scale, the strange laws of quantum mechanics start to interfere, causing problems like heat buildup and electrons tunneling where they shouldn't, you know. The next great leap in computation will not come from making today's computers smaller. It will require a completely new kind of computer, a quantum computer. These machines are not just faster versions of what we have now. They operate on entirely different principles, harnessing the bizarre rules of the quantum world: superposition, entanglement. A quantum computer could solve certain problems that are impossible for even the most powerful supercomputers today. But building a useful, large-scale quantum computer is one of the greatest scientific and engineering challenges of our time. The quantum states that these computers rely on are incredibly fragile. The slightest vibration or change in temperature can destroy the calculation, an effect called decoherence. We are currently in the very early days, like the vacuum tube era. We can build small, noisy processors, but scaling them is monumental. Our current understanding shows the promise, but it might not overcome the hurdles. This is where new physics could provide the key. Humanity has always looked to the stars with a sense of wonder. We have walked on the moon and sent robotic probes to the farthest reaches of our solar system. These are monumental achievements, built on rocketry and orbital mechanics laid down by Newton. Yet, the stars remain impossibly far away. With our current technology, a journey to even the nearest star system, Proxima Centauri, would take tens of thousands of years. We are like islanders who have learned to build excellent canoes but dream of crossing the vast ocean. Our chemical rockets are simply not up to the task. To truly become a starfaring species, we need a revolution in propulsion, a new way to interact with space and time itself. Einstein's theory shows gravity is the warping of space-time by mass and energy. Warp drives, wormholes, staples of science fiction, have a basis in real, albeit speculative, physics. A warp drive wouldn't propel a ship through space. It would, in theory, compress space in front and expand space behind, moving a bubble of space-time with the ship stationary inside, without violating the speed of light. The problem, it would require exotic matter with negative mass or negative energy density, something our current physics does not allow or know how to create. Wormholes are valid solutions but thought to be unstable and likely require the same exotic matter to hold them open. Finding new physics could be the difference between mathematical curiosities and engineering blueprints. It could provide the breakthrough to control gravity itself. If we could do that, the vast distances might become manageable, and humanity's future could expand into the cosmic ocean. The discovery of new fundamental laws of physics would not just lead to new gadgets. It would reshape our entire society in profound and unpredictable ways. Every major scientific revolution in the past has done this. The laws of thermodynamics gave us the steam engine, the Industrial Revolution, changing where people lived, how they worked, how nations were structured. Electromagnetism gave us electricity, lit our nights, powered factories, created the global communications network. New physics would ignite a similar, perhaps greater, transformation. Think about the economic and social shifts. A limitless clean energy source would radically alter geopolitics, moving power away from fossil fuel nations. It would make clean water and food production cheaper and more accessible, potentially lifting billions from poverty. At the same time, disruption, industries become obsolete, jobs are lost, new industries are born, requiring new skills. There is also a crucial ethical dimension. New physics could unlock immense power. And with great power comes great responsibility. The same discoveries that power our cities could create unimaginably powerful weapons. The same quantum computers that could cure diseases could also shatter global privacy. We must develop a framework of wisdom and ethics, not just scientists, but everyone, building a global consensus to ensure benefits for all humanity. Ultimately, a new understanding of the universe could change how we see ourselves. Like Copernicus and Darwin reshaped our place and origins, revealing deeper connections to the fabric of the cosmos. It could answer where the universe came from and the nature of reality, inspiring new art, new philosophy, a new sense of shared purpose. The journey will be hard. We don't know where breakthroughs will come. Colliders, telescopes, galaxies, or a pencil and paper. To make it possible, invest in curiosity-driven research, support scientists, build labs, fund bold experiments, collaborate across borders.